There's a mailing list which you can sign up to. So if you want to be signed up to this, generally, if somebody emails me with a question, I'll ask them directly if they want to be signed up. You can also just email me. That's just for announcements and new versions. So you won't get spammed with discussion and so on. It's just an announcement. And user support means, so this is free and open source software. If it breaks, you get to keep the pieces. Not only do you get to keep the pieces, but if you email us the pieces, we will look at what went on, where it broke, and try to help you. Yeah, this goes regardless of whether you're collaborating with us or not. Yeah, of course, that doesn't have to be. It's completely stable and it works. Okay. What else do you get? You get a set of scripts. So these are scripts that are interested in plotting graphs, collating results, maybe all kinds of things. Now, the difference between what I've called here scripts and core programs are that the scripts, you're meant to copy them to your working directory and modify them. So this is just a cutout of one of these scripts, and you'll notice here there's a comment that says default argument / feel free to override. And I really mean this. You're supposed to put in your preferred default options in your whatever your project is, so you don't have to type them in. And you're supposed to do bigger modifications, so whatever you like. These are really meant to be the starting point for your ideas. The real programs generally have line-by-line options that you can tell it to do things, but if you wanted to add a new feature, that would be hard. You'd have to modify the source code, which is also encouraged. Finally, you get something called libCrystFEL. This is a shared library which exposes the high-level functions. So, for example, there's a function to index this pattern, or calculate the partialities of these reflections, or various other things. It's not meant to be like a low-level library with stuff, for example, CCTVX is meant to be. So it doesn't, although it does contain routines for things like handling conflict symmetry and cell geometry and rotation and stuff like that. It does happen to have those, but it's only for completeness. That's not what it's meant to be. It's meant to be. What is best illustrated by this possible application, which is if you wanted to use CrystFEL for an online data processing workflow, for example, in an online facility processing thing, you could write a plugin to their facilities data processing framework that calls these CrystFEL routines. So that would save going to pull out and run the program. Documentation is really the API on the website. Yeah, okay, so this external programs can use this library as well, and there are some core programs that also call this library within CrystFEL. And we just draw this boundary of what we call CrystFEL and what we call external. So where can you get it? The simplest place is just to go to the website. So there it is again, but just seriously, just type Google, just type CrystFEL, get it straight. You have a choice of download options. So there are what we call release versions. These have version numbers, for example, 0.8. These have been tested with a whole series of regression tests. So we run it against old data sets to check that we're still getting the same result that we were before, check that nothing's broken. Hopefully the results improve. Yeah, we want to know that we haven't made any mistakes or suddenly made it not work for a whole small bit. If you are feeling brave, you can go to the Git repository. This is the version control repository. Gives you the very latest code, so that's up to the minute what we're working on. It might be broken. Okay, we might have made some changes that breaks everything, and we haven't worked through the consequences yet. Or it might be awesome because it may have new features that you need, or you might have just added something that improve the data quality. It's slightly harder to install because you need this auto tool stuff, so don't worry about that too much. If you don't want to go all the way to using the up-to-the-minute repository, but you do want to get the latest code, there are also snapshots on the website. These are packaged in the same way that the release versions are packaged. They are taken from the Git repository at times when we decided that it was sensible to do that. They're as easy to install as the release versions, but they haven't been through the test versions. If you use Ubuntu, Red Hat, a few other distributions, or Mac, there's a Mac board, so the packages you can just install directly. quite soon it will pop up in the Debian repository. So if you use Debian, you'll just apt-get install this thing. But for most people, we'll say the release version. It's also pre-installed in a number of places, for example, Slack. We use a pre-installed version of something, so you don't have to worry about it. Okay, this GPL thing, it's what we call free as in freedom. It's also free as in free beer, because it won't cost anything. Now, this freedom means you have these 4 essential freedoms. So you have freedom to use the software for any purpose. That includes commercial use, so there's no distinction in academic to commercial. Everyone can use the software. You have freedom to study how the software works, because you've got source code. You can change it to fix bugs, add features, break it horribly, whatever you like. And you don't have to send us the results. And you have the freedom to share it, even the modified version. It's for example, in collaborators or whatever you want. There are no license forms to sign or send to us or anything like that. And the GPL ensures that these rights are never restricted, so this will always be the case. Okay, so in IndexLogic, there is a fully automated pipeline for processing collection patterns. We generally have so many patterns to process that it can't really be supervised manually. So it would be absolutely great if every one of these 100,000 patterns really get the best out of every single one. That would be fantastic, but it would take forever. So we have an automated pipeline. We run many thousands of patterns in one job. It's parallelized, so it will run quickly. There is a choice of methods. So there's a choice of methods at various stages. So if we look at this pipeline, we start in the top with a fraction pattern. This is in HTML5 format, which is a common scientific data format. It has language bindings for everything. So it's Python bindings, C, MATLAB. I think everything has got the option to use HTML5. So don't be scared if you're not familiar with HTML5. We do a peak search, so there's a choice of methods here, how to find peaks. Pattern is an index, which means we give these peaks locations to external indexing programs. So at the moment, there's an option to use LossRun, Dirac, or XDS. What we're doing there is taking advantage of the developments from these programs and getting really good indexing results. So rather than implement the algorithms directly within CrystFEL, we run this route with the programs, and it seems to be very successful. We check whether the cell that comes out of indexing is the same as what we want it to be. If it's not, we go back. You go back to the indexing step and try a new indexing method. Or we can just switch the pattern. So we couldn't make it do that. Once that's happened, we check that the peak locations in the pattern agree with the indexing solution. So that means that we haven't found some crazy indexing solution that seems to have the right parameters but is just wrong. Again, if that doesn't succeed, we go back to the indexing step or to the final try step. Then we predict the spots that should appear in the pattern, given the crystal orientation and some geometric parameters. And then we integrate those predicted locations to get the final integrated quantities. And the output is this thing we call the stream. And the stream is plain text, so don't be afraid to open this in your favorite text editor, have a look. There's all kinds of useful stuff in here if you want to develop some new technique or to study some distributions. It's all in there, it's just text. So please look. Tip here, use less Unix program, less, not gedit, which is far from very much. Question? Two slides. So here's an example of how you exercise your choice. So CrystFEL is a primarily command line based program. So you need to be afraid of this. It just means you type the name of the program and then options, for example, -- peaks equals HTML5 means get the peaks from inside the HTML5. This is because Cheetah, which Anton just talked about, can write peaks that it found during its peak search procedure, hit finding into the HTML5 file. And we can then retrieve those and use this in indexing. And you can also say peaks equals Xiaf. This means a cipher algorithm, which is for many historical reasons. But that's built into CrystFEL, so it will then use its own peak search to find peaks again. So that's how you choose your peak search method. You then have to tell it how to index the pattern. This is a bit more complicated, but follows the same principle. So you say indexing, indexing equals method 1 equal to as many as you want. So a method might be something like this, mosfilm --raw lat. So what does this mean? This means invoke mosfilm to index this pattern using the peak search. We did that. Raw here means skip the step where the unit cell parameters will be checked against this reference. So if you have this option raw, you don't need you don't necessarily need an input UV file to tell you the expected cell parameters. There's also lat here, which means to take the Bravais lattice information into account. So, for example, we might want mosfilm to only give us tetragonal primitive lattices, and if the reference that we give it is tetragonal primitive, when we give it this indexing method, it will skip the check that the parameters are what we expect, but it will find only a tetragonal primitive cell. So this can be useful. Okay, so a different method might be the same, so it might be mosfilm axes lat. So this is the same, I've just changed raw to axes. So now we're checking the unit cell parameters against the reference as well. So this is a more stringent test. You can also do mosfilm raw no lat. This means don't check the unit cell parameters and also don't use Bravais lattice information. So this is completely open-ended, free indexing. Whatever mosfilm thinks it is, that's what we get. You can call Diracs different indexing. POM fits in the slot for raw axes. It means the same as axes, so check the unit cell parameters against the reference, but allow it to double, halve, and lattice vectors together whenever to get it to fit. Because, for example, sometimes the indexing method might be confused and give you a unit cell that's 2 times too big. And then if you use this option, it's allowed to halve it. So if you halve it, it's obviously less common. Just halve it. And we have no lat, so we're not using Bravais lattice information. If you've ever used the program Diracs, I think it's mostly a small molecule program. You'll find Diracs can't actually use lattice type information, so this is the default, in fact it's the only option. Don't be too afraid of this because IndexImaging will correct your options. If you give it something that doesn't make sense, it will correct it for you, it will tell you what it's done, and it will generally do what it's done. So let's say you do open-ended free indexing. You can then take the output stream and open it using Unit Cell Explorer, and you'll get a window that looks like this with 6 graphs. Graphs are showing you the histograms of the values for the lengths of A, B, and C, and it also offers you to hopefully you see a nice sharp peak at the values you expect. The Cell Explorer can handle the fact that the cell might be centered, so actually in this case it's eye-centered, body-centered. And we see we've determined parameters here. You can do things, you can drag these graphs around, you can zoom in. You can select, for example, a range, like, say for instance there was a secondary peak somewhere. You can select that secondary peak and it would show you values in the other graphs that have that value for the same. And you can also fit, just as a Gaussian fit, to give you the mean and standard deviation of the cell parameters. So that's what you can work with. Yeah, so I'll have a chance to cover this later in the tutorial. If you do have a known unit cell, you can still do this, you should still do this, and just check that you're not being a bit too sharp with the cutoffs, just check that you're getting it. Okay, you can use a whole range of indexing methods, one after the other. So typical use might be, this would be the deluxe option. So indexing equals Diracs, mosfilm, yes, mosfilm raw lat. So the first thing is to use Diracs using the defaults. Now the defaults, it tells you in the manual page, it's what defaults are for everything. The defaults for this are to match the unit cell parameters. So we try Diracs, we try to fit our reference cell, hopefully that works. If that doesn't work, we will run mosfilm, Or again, using also the defaults. The default for this is to match subparameters, of course, but also to use the universal information. Then we try XDS, again with indexing. You have to have these programs installed. If after that it's still somehow not indexed, let's try getting MOSFEL to look for the lattice type with any parameters. So we turn off this cell. So we're saying, well, maybe the cell is still orthonomic, but maybe the cell axis has become 20% larger. So this will then get picked up by this method. And if after that it still doesn't index, last resort, just do or whatever it finds, let's see. So you can build like a processing pipeline. They'll be tried in the order you do. Now, if you do this, all of the results from these different methods will be together in one stream. So how do you separate them out again? Well, because it's just text, you can write a quick script just to separate out bits you need. If you use the Unicell Explorer, I don't know if you notice at the top here there's a little button that says show results from. In this case, there's only one button because we used only one indexing method in this example. But if you had a range of indexing methods, you'd have multiple buttons here. And the default is can all be switched on, but you can unselect them and see only the results. Right. We need a bit more information than what's in the H255. And this comes in the form of the beam and geometry files. So when you run indexing G, you give it /beam equals, this is the file name of the beam file. Now, inside the beam file is a very simple 7-line file. It contains the bandwidth, divergence, and this profile radius that I'll run to. That's the radius of a ground reflection in this space. These parameters are important for the spot prediction step, so when we calculate which reflection should appear in the reflection pattern. So we might have to tune these a bit. We also tell it what the energy per photon is in electron volts. In this case, we've given it not a number, but this thing /LCLS/photon energy ED. This is a path into the H255 file. So saying this H255 file contains the individual photon energy for this pattern. So that allows the photon energy to fluctuate from shot to shot, or always use the correct method. There's a scale factor as well, which is the default is 1, but we can increase or decrease that if you know this value to be systematically wrong, as appears to be the case. Recently it's come to light that these values might not be spot on, and the correction factor is needed. Because the beam files are common to all programs in CrystFEL, including the simulation programs, there's also the fluence and the radius of the X-ray beam. These will be completely ignored for indexing, so only if you want to simulate you want to tell it this the photons are to calculate the realistic signal. I should mention these beam files will probably go away in the next major version of CrystFEL, which will be 0.6.0 in maybe a month, couple months, in favour of command line arguments for specifying some of the things, but also automated calculation of the optimum values of these conditions. So expect the beam files to they're often what are scary are geometry files. So these are given in the same way with geometry equals geometry files. These things are a menace in some case. Where do you get one of these? This is the file that tells you how to get from whatever's in the H255 file to the real geometrical location in space. So firstly, because the CS-PAD detector is so complicated with its many tiles, that's the first thing that makes it difficult. The second thing that makes it difficult is that a fine refinement really does help, so it's worth having a good geometry. Although, as I said, it's surprisingly robust to inaccurate geometry. So many of the papers so far haven't had the most precise geometry in the world, and it's still being refined considering some structures. So don't get too scared. Yeah, the second thing that makes it difficult is this geometry can vary during the course of the experiment. They kick the detector along. So what do you do? Okay, we'll read man, CrystFEL underscore function. We'll explain what's in this file. There are templates distributed with CrystFEL that you can use to base regression. Ask a friendly protein crystal screening collaborator, blue light scientist, or us. We'll try to get you a geometry file. Recently, there's also this calibration mode in HGFC, so that means you can switch this on, and then you can move panels around to get good. And also in this upcoming major version, there'll be a geometry refinement tool that will use automatically give you a less accurate geometry. Okay, so that's geometry being files. Right. So after the indexing, there's the integration step. CrystFEL predicts the spots according to this information in files. Now we integrate. Again, you have a choice of integration methods, and you must specify which method you want to use. They look very similar to the indexing methods, but this time you must only choose one. So we say integration equals. An example method might be something like this. So rings, sat, sem. So this means rings means use the basic summation integration with background function. Sat means include saturation reflections. The default is not to. Sen means to center the integration position on the peak first. Another option would be off2d-sen. So this means use two-dimensional profile fitting. Exclude saturation reflections. This is the default, so you don't have to add it, but you could add it, so no snap. Work. Yeah, so you take all the strong reflections and you add them all together, and that gives you a reference profile, and then you fit that reference profile to all the other reflections. So the idea is that it's done on a per pattern basis, so it will be the strong reflections from that pattern put into all reflections from that pattern. The idea is that you're only fitting one parameter, intensity, rather than trying to measure all these peak values, these fixed values. So please experiment with these methods and let us know what helps. We actually find often the basic ring subtraction integration works the best. This because it's a bit more robust to poor geometry or maybe slightly dodgy predictive location. The centering you have to be a little bit careful with, because that allows the algorithm to go looking for signal, and if there isn't signal, well, there's always a background, right? So if it uses only bright pixels to center the function, well, these still happen in a large data set reasonably often, and that can give you a bias in the data. So the centering I'd expect would help for strong reflections, but it might hinder weak reflections. And it might, there's a suggestion that it could give you more leeway for phase legislation. So be a bit careful with these, but yeah. There are also integration diagnostics. So you can say int diag equals something, and the something can be none, which is the default. It can be a set of indices, for example, 4.3.5, that's h. Be random, implausible, or negative. And what this does is, when this scenario is encountered, you will see on your terminal something that looks a bit like this. So it's a visualization of the integration box. You can see the peak values, you can see the fitted background, you can see what it thinks the intensity is. If you're using profile fitting, it will show you the reference profile. So you can see what's going on. A good use of this is if you choose the implausible option, this will show reflections which have intensities less than -5 sigma. So ones that are really negative are more than they should. 5 sigma should basically never happen, even though it's there. So if you see this, this is implausible. In fact, CrystFEL by default will reject reflections that are negative and more than 5 sigma. It will print a warning. So if you see this warning popping up, you should do int diag equals implausible and look. What's always been the case when I've seen this happen is that there's been a bad pixel that's hasn't been masked somehow. So maybe you need to change your tutor options or mask out the region. So there might be a single pixel with zero intensity. In the background are many thousands of photons, and this will give it a very negative value. It doesn't happen routinely. The integration results do seem to obey the expected statistics according to the signals. Okay, great. So a nasty secret of FEL, or serial data rather, is the indexing ambiguity. This, I think, many people are familiar with. It's when you have a crystal structure, for example, here's a crystal structure I made out of arrows. The diffraction from this schematically is a lattice that looks like this. Of course, these reflections will have different intensities. If I turn the structure upside down, schematically, geometrically, the diffraction pattern looks the same. Now, the indexing method uses geometry. Doesn't look at intensity at all. It just looks at the spot positions. So it can't tell the difference between these two crystals. So the index gives the orientation of the lattice up to the symmetry of the lattice. Now the symmetry of the real structure is lower than the symmetry of the lattice with no helium. So the indexing will mix up these orientations. So this applies in 3D as well. Here's what will happen if you don't deal with this. On the left here is a zone axis. This is actually made with render HCOM. If you squint at this, you'll see it has a twofold symmetry in this projection. If the indexing ambiguity is not resolved, what you'll see is this. This, if you squint again, has a fourfold symmetry. That fourfold symmetry is artificial. If you put this into a normal program, what it will tell you is that the crystal is twinned. Crystal is not really twinned. It's an artificial artifact. Now, Wolfgang Brain very soon will be telling you all about this, which we showed in detail. In CrystFEL or on the website, there's a table that you can look up your favorite space group. It will tell you whether it's subject to this ambiguity. So it's a useful quick reference. There is an algorithm now, thanks to work in Wisconsin, to resolve this ambiguity. That's implemented in CrystFEL in the program Ambigator. It's really easy to use, it's really fast, and huge thanks to Wolfgang Brain for coming to Hamburg for a really intense couple of days implementing this algorithm to his very high standards of mathematical rigor and efficiency. It's really fantastic. Here's how you use it. You do an Ambigator program, you give it the input stream, you give it -O and then output. So this is the output. It will output another stream where the orientations of the crystals are being flipped for the ones that were wrong in the index. You give it the actual symmetry, so I've given it as a point group, 6/m. Note that I've added a center of symmetry here. The symmetry of this crystal is not 6/m, it's 6. You can't have it at an m in a plane structure. What I've done is I've added a center of symmetry for the point group, and that means we're considering 3 delta pairs. That's generally how CrystFEL works. So you tell it the symmetry of the image or consider. -W and then the apparent symmetry. So the apparent symmetry, if you have this ambiguity, in this case, is 6/m. So that's adding some extra twofolds. You can also give the ambiguity operator directly using -- operator. You can give it, for example, k, h, k, h, minus r. So that's useful if you have a really weird ambiguity. So there's some ambiguities that don't fit into this one. -J8, that means use 8 threads calculations to go a lot faster. And there's a resolution range, low res and high res imports. These are in angstroms. The resolution range to consider. This has to be big because you have to have enough reflections contributing to the calculation. It shouldn't be too big. I guess Wolfgang might explain this, but it's the reason is because it's a correlation coefficient-based algorithm. So it's if you flip the pattern, does it correlate better or worse? And then there's a large average of correlation coefficients to get through the noise. If you have a very large resolution range, well, low resolution reflections from any structure are strong. High resolution reflections are weak. That's just the normal scattering factor. That will give you a certain amount of correlation, even if the orientation is wrong. So by restricting the range, you look at a narrow shell of reciprocal space. where that fall off isn't so severe, and that can then help the contrast between the right and the wrong orientation. So just play with this. Once you've done that, you can merge your intensities using CrystFEL. It's very easy. Give it the input and the output HTML and the symmetry. So it will merge symmetrically. If you don't want it to do that, you can just do it -1 or again, notice that I've added the center of symmetry here because in this experiment, this example, I wanted to merge for both. So if you want to keep them separately, give it the real symmetry, so -1/6. Of course, then you would have half as many measurements per reflection. So there's a penalty. The output from this is a text file again. In fact, almost everything on this file is a text file. So this can be easily imported into most structure solution programs. Alternatively, in CrystFEL, there's a great NTZ, great XFEL, but not it's just if you are confused about what to put in this symmetry thing, just look at man and CrystFEL, and there's a list of all of the right. There are a lot of options to do lots of different things. If you go on the CrystFEL website, look at the best practice, it's right here, and it's so far. There's a list for every stage of what should you do. Should you definitely use this option? Should you definitely not use this option unless you're testing something? Some of them it says, try this option, see what happens, might be good or bad, maybe you never know, perhaps. Watch out for some gotcha, and so on. So have a good read about page. We'll continue on useful. Okay, so future developments, look at what's to come. Soon after this workshop, unless we find some showstoppers, we'll be releasing version 0.5.4. This will be an incremental upgrade as minor new features and so on. In fact, the version, this release is actually all ready to go. It's been through tests and everything. I just wanted to hold off the release because you can guarantee that if I did this release before the workshop, then something would come up during the workshop. Something stupid is awesome. So we're going to get you guys to test this version. We're really sure it's that version. In a few months, there will be version 0.6. So this will have some bigger changes. So as I mentioned, beam files will probably go away. We'll probably get rid of all these -y options because in most cases this can be determined automatically. The indexing algorithm knows what symmetry it can tell. It can discriminate between, so it knows what the kind of symmetry should be. So it turns out there are very few times when you actually really need to implement that. Currently, CrystFEL expects there to be one image, so one X-ray pulse, one event in one HTML file. This is bad because this was load on the file system. This will remove it. What we're moving towards is having multiple images in one file. So you have maybe 1,000 in one big HTML file. That's much more efficient. It will enable us to use Slack's HTML. These are HTML files that the Slack system can produce for you users directly. So if you either don't want to use it at all, or if you want to use Slack's bit-finding thing in reference to a tutor or a class, you can do that. So the new version will support that. That's all ready to go as well. We just need to put it in the test. Alright, more future developments, multilattice indexing. So the core of CrystFEL since forever can deal with any number of crystals per pattern. Now the limitation is the underlying indexing algorithms. Because we've taken this path of calling out external indexing programs, rather than having our own algorithms. None of those currently can index. So this is a shot when there are multiple crystals in the beam at once, so overlapping reflection patterns. And the algorithms won't deal with this. At best, they will just give you one glance. So coming soon in this new version, well, there'll be the ability to use them to new developments in loss form. There'll be an interface to this program called Phoenix, which is related to grain spotter /TotalCryst mixing program. This is for very strong multiplexers, so like 20 crystals. It's a very cool new algorithm based on this thing called Rodriguez. And also multiple lattice mixing using an internal mechanism. So this has been a contribution from Takanori Nakami from Hull, the Moscow group in Cambridge. And simply by subtracting the peaks that have been accounted for already and going around again. And of course, the great advantage is because of the structure of CrystFEL, you'll be able to do all of these all together and get more kind of robust. Yeah, so I'm including this in the future work because this is needs a bit more scientific work before it's generally applicable. But the code, as I'll show you, has been around for ages. This is taking into account these partialities. Now, this has been explained very nicely in what partiality is. We want to compensate for partiality when we merge the data. So currently, we just pretend all the partialities are one. So what we want to do is say, well, actually, we know that this reflection is a long way from Bragg, this one's close to Bragg, and then compensate for that. So we would expand, increase the intensity of the one that's a long way from Bragg to compensate for the fact that the program to do this is called partial editor. It works like this. You give it the input stream and an output HTML file and symmetry. So far it's exactly the same as HTML. You then give it a model of it. So model equals here, sphere. So this is a sphere partiality model. And there are options here. So you can have sphere, you can have Gaussian, which are model reflections of Gaussian. SC sphere is something else, what I get to. Thin, but yeah, just different ways to model partiality. And unity is the default. I mean, these are the basic method way just pretend equals them. And a number of iterations of this thing called CrystFEL, which I'll explain in just a second. Note that the detector geometry, beam files, and the images themselves are not needed, which I think is a very nice feature. Okay, so what's this doing? The basic scheme for what I'm going to describe has been given in, well, it was specified in the basic scheme in the context of serial femtosecond crystallography is in this paper in Royal Society. So here's my visualization of diffraction with these little spots. These are the 3D reflections in physical space. Green is the volume excited by the EVOT sphere. And as I said, what we're trying to do is compensate for the fact that, for instance, this reflection here is just being cut, whereas this one is being hit right in the middle. So this one would need to be compensating. So if we have the intensities measured from the diffraction pattern, and we have crystal parameters and beam parameters. With crystal parameters and beam parameters, we can make partiality estimates. That's the partiality model in this box here. And if you combine those partiality estimates with the intensities, you get hopefully full intensities. If you want to just do this, just apply the model, you can just set iterations equal 0. So just write we now do this for many reflection patterns. We get many measurements of the same reflection and add them together, give us a hopefully good estimate of the average for the testing of that reflection. Then we do refinement step. That's where we go back to every pattern in turn and we refine crystal parameters and beam parameters using the intensities from the patterns, comparing them to the average full measurements. So the least squares fitting regime gives us improved crystal parameters and improved beam parameters. So if we get better parameters, hopefully we get better data, and we iterate around this whole thing a number of times. So in simulations, this works. On the right is just a graph of how close we get to the correct answer, because we know the correct answer in the simulation. And you see very quickly with only one iteration brings you to this line here, it's already taken a huge jump from this line here, which is what you get with basic Monte Carlo unity model. Note actually that already just applying the model gives you these lines here. So the initial crystal parameters just from indexing seem to be quite accurate, in this case, accurate enough to make some good partiality estimates. And then we refine that, we get basically down to R equals close to 0. Yes, it works. On the left, what I've shown is a nice visualization of, on the x-axis is calculated partiality, and the y-axis is observed partiality. Calculated partiality is for a given reflection, each dot here corresponds to one reflection. Calculated partiality is what the model says the partiality of the reflection should be. Observed partiality is that intensity from the reflection pattern divided by the full intensity with the usual scale reflection. If this is working, what we should get is a straight line. What we calculate the partiality to be should be exactly what they need to be. So on the left is before refinement, so it's good with how. And on the right is after one cycle. You can see they're now concentrated on this line right from the middle. So that shows that it's working. So why have I put this in feature work if it appears to work? Well, the reason is it works fantastically on simulations of different kinds, really, really well. But to make it work on real data is quite a lot harder. We're assuming, in this case, that this is the dominant source of power, partiality, which is not, at least to me, is not here. So I admit I haven't really made this work. But please give it a try. It turns out Mona, who I thought was going to be here, actually isn't, who works on the CCTVX side of things. She has successfully made this work for real data. So that's absolutely fantastic, because that means that it's good as possible. So hopefully very soon you'll be seeing this generally applicable for every data set, and that should give us a boost in quality of data we get or reduction in quality. Okay, so shameless advert, some PDB entries which use CrystFEL. These are just highlights, there are many more. We've got filter system 1, first best select experiment ever. As has already been mentioned, doing serial crystallography using a synchrotron line, that's in there. So just highlighting that CrystFEL is not limited to FELs, certainly not limited just to the estimates. This gadolinium phasing with lysosome, which is that. Flow system 2, and a fugitive S3 surface state. FEPS and B natively primitive thing. This is a really nice example, I think, because this extra density that Carol mentioned in the propeptide, this wasn't expected at all. So Carol is solving this with Carol's PhD project, and he solved the structure and had really nice density for the whole structure, but then saw this extra thing, what's this? What's this? And it was completely unexpected, and it was, yeah, he's actually this inhibiting you. So that's fantastic. Then there's a couple of GPCRs solved using with ligands, solved using this lipidic phase injector. So this convention reduces the amount of symptoms. In fact, there's about this many. So this is just a list of references. This is all on the website. So if you want to read about these applications and how the applications are varied, so you can just get these from the website. So that's been done for shameless advertising and indeed for my talk. I hope you're looking forward to giving this a try tomorrow. Yeah, then thanks very much. Great question.
So then we can what?
How close are we to using the methodology to be sufficiently accurate to use that information in the past in S-band files? So the detective methodology is sufficiently accurate to allow that. We will eventually.
I think it's quite hard to answer that question from the data we've had so far. This simulation results, if you read the paper for this, which of course you have, you'll see this simulation is based on calculating partial intensities and then adding noise to the unit cell basis vectors to simulate an inaccurate not quite knowing initial geometry, and then to demonstrate with different levels of noise whether we can get back to the right answer. And that indeed works. The next step was to say, well, how much noise do we get just from indexing that? So what I've done since then is to draw in the dots into diffraction patterns at least these locations and index that. So that gives you an unbiased estimate of how accurate your rotation will be from indexing, and actually works even better than this. So I think just from indexing, the orientations are good. What I don't know is how much the errors that we have compromise. But I guess that can be tested. But the beauty of this post-refinement technique is remembering here, it doesn't need the geometry. So we integrate the reflection. As long as we've made an accurate measurement that the intensity of, say, the 5.0 reflection is this many photons, plus or minus this many photons. As long as that's accurate, that's all we need. If the geometry is then not needed. I haven't tried it. I have tried simulating using pattern sim, which does almost the same as what European does in that. You can give it a try. Yeah, the hard part, what I find when it doesn't work is not that the refinement doesn't work, it's that just applying model doesn't do as it should do. So it doesn't. But in the, yeah, I've got some graphs. Needed.
So it's not quite clear to me what you're doing there. Are you simulating a large number of atoms which you then storing together?
In this case, this thing. Yeah. So I wanted to test in isolation the post-refinement method. So I calculated the geometrical model can be used just given an input with fully integrated reflections. You calculate random orientation and calculate which reflections should appear in that diffraction pattern and what the partiality should be. And then you multiply the partialities by the intensities, and also there's a scaling factor, there's also those to give you a partial intensity. That then goes in the stream, and then that goes in.
So for instance, what we call the observed value or something like that, equal to diameter, for each cycle, you could be taking the corrected intensity corrected out of partiality and taking the average, that would be the temporary observed.
Yes, that's exactly how it works. Yeah. There's no reference, no external. Does that answer?
Then of course there's a question of what you do with how you do it.
Yeah, so if the integration is poor, then it's the worst.
Okay, if there's no further questions, we can adjourn for lunch.